I'll just call it this. Okay, hello. This is my talk. This was not the intended use of the internet. So I think it's just worth starting off and saying that computers are awesome. When you think about it, we taught rocks to think, which is kind of cool. And the internet is awesome because we taught basically our copper wire. We got our copper ore to carry information around the world for us. In fact, pretty much all of you probably learned about this thing from the internet, which just kind of, you take a few steps back, everything is kind of really cool. The internet grew from just a bunch of PDP-11s glued together with copper wire, and mostly the telephone line, the long distance telephone line network. And just people just kept adding stuff on and on and on, and we have the giant mess that is today. It's also kind of a demonstration of standards working really well. For a brief amount of time, there was kind of flux in how the ARPANET network, the wide area network, was supposed to work. People hadn't really formalized on things like IP yet, but we managed to actually get through that. And now, I'll put it this way. When you go to different countries, we use different plugs and different power standards. In America, we use 120 volt. They use 120 volts. And in Britain, we use 240. The rest of Europe uses 240 and a different frequency. And so I just think it's kind of amazing that, given that they couldn't standardize on something as roughly standardized as electricity, we've managed to get computers to talk the same protocol. Protocols such as the TCP, which is basically what most of the communications go over, DNS, which is what translates things like Google into numbers, Secure Shell to fix the computers that aren't doing those two things very well. And all of this is manned roughly by a consortium called the IETF, the Internet Engineering Task Force, which is a fantastic name that makes them sound very strong, and I don't know, just it's anything that ends in task force is incredible, I think. And they have all sorts of stuff. There's RFC documents for the evil bit for suggesting that hackers should select a specific bit in a packet to say when they're doing dangerous things. And there are more important security things like transport layer security, which is what is making sure that all of our stuff is secure, which is important. I guess my point is you see the IETF as something like this. Very well organized, strong meetings, glass tables, everyone's talking about the most important stuff. That is definitely not what the IETF looks like. It looks like this. It's basically just a bunch of dudes in a conference who just sit down and talk about what is currently broken about the protocols that we are using and how we can make them better. Unfortunately, it is mostly dudes. This is actually IETF 99, yeah. It's actually kind of depressingly... It's depressing. So my always thought is when I read a protocol, when I read an RFC, I'm well, what else can you do with this? So, you have DNS, which resolves names. You have, various other protocols which do various other things. What else can you do with these things? Recently, within the last year, I became an ISP myself, which has been the stars aligned. I was able to get all the stuff required to become an ISP. This has the fantastic things that I am my own ISP now. I answer only to myself. I have IP addresses which are questionably, concurrently mine. I get to take up memory in everyone's extremely expensive routers, which is always a nice feeling inside. And most importantly, if I do something bad on those IP addresses, either probably by mistake, I don't intend to do bad things. Just sometimes people mispass my actions as bad. I am the only one who gets the email for that. I don't have to explain it to a provider, which is very handy because a lot of the time providers aren't very welcoming towards these emails. So I can generally tell myself off when I've done something bad.
You get a lot of them.
We'll get to that later. The question was, do I get a lot of those? So we'll start with the first thing that immediately was obvious when I learned about ping was how far can you just send 3 billion of these? To just see who else is online? The answer is yes, you can. You can produce these beautiful maps called Hilbert curves. Every pixel here, the projector is not high resolution enough to display it, but on the original image, every pixel here is a /24 of IP addresses, 256 IP addresses, and it goes from blue, there are 1 or 2 IP addresses alive in that region, to red, which is all of them respond to ping. And it's very faint, but you can roughly see I'm highlighting what the blocks are originally called. They're old legacy ones for when the United States Postal Service had, a couple of thousand, hundreds of thousands of IP addresses allocated to delivering post. I'm not really sure either. But yeah, you can also do this over time. So in this case, I pinged the entire of Asia multiple times every 30 minutes over a 24-hour period, and sort of just saw how the internet like breathed in and out there. One of the really cool things is you can see the small GIF, the most bottom one, most lowest resolution, I guess is the best way to describe it. And that's a pool of IP addresses in Taiwan, for which the only way I can get a description of it is this is a DSL pool. So when people reset their modems, they just increment another IP address, right? Assuming it's not taken. And clearly they're not like full enough subscriber volume, which means that you get this beautiful animation between the day of people slowly but surely like resetting their modems or like their power going out or something like that. And you get this really nice like refreshing cycle as you walk up the diagram. I just think this stuff's beautiful. Like it's, you have the internet right here. This is questionably everyone who has internet. I think that's really cool. Of course, you do commit some internet sins by doing this. First of all, like 3.7 billion things just got a packet that they, didn't particularly need. And Asia was getting a packet every 30 minutes minimum. Total abuse emails, can we imagine?
It's Asia, 0.
Correct. No one actually cares about getting pings. Apparently, that's just such a low level of care now. I was kind of disappointed. DNSFS. So DNS is the thing that we use to like turn Google into just numbers that our computer can talk to. Most DNS setups look like this in the real world. You have your home network, the boundary. You have your local DNS cache, which is normally your Fritzbox or router or whatever you call it, Soho router. You have, your firewall to ensure that, stuff stays within your network. But that DNS cache will be pointing to some other authoritative server. This is like what 8.8.8.8 does. And then that 8.8 goes and does the actual authoritative lookups, because that requires some logic, which most of the time small routers don't want to do. So my thought was, can we be sure that this black line really exists? Like that the rest of the internet just can't get in and just use your cache for free? And the answer is, I sent another 3.7 billion packets, about 266 gigabytes of bandwidth. But actually you can see I'm getting a decent return here. I say a decent return. I'm getting a return here. I got 18 gigabytes of DNS back, which I think is actually quite impressive. That's a lot of stuff that's misconfigured. That's a lot of firewalls that are not working. So roughly speaking, the scanning system just blasted out packets into the ether. Some of those ones just so happen to be open resolvers. I got response back from my domain of the things that are querying me, but also I got response back on the scanning system, so I have data in both directions in case there was packet loss. Internet sins. Another 3.7 billion things got a UDP packet that they weren't particularly asking for. The difference is with DNS is that DNS servers, if they are configured correctly, but not firewalled, they will send a log line for every single time they get a packet like this, which means that what I'm doing here is way more visible to network providers. So could we potentially guess how many abuse emails this would have netted me?
0.
3. One was a robot. One was a Canadian university computer person at the head of the physics department saying, "Can you please not generate so many log lines on my computers?" Which I said, "Yeah, sure, sorry, I won't do that again." And the third one was this beautiful email for which a Scottish person tells me to fuck off and die, and then citing the log line that he found on his computer. I initially thought this was pretty funny that he was sending this to an abuse inbox. I was tempted to send him back an email that says, "Wrong kind of abuse, mate." But I just never responded to him. Just let angry people be angry on the internet. So yeah, this is roughly how the DNSFS idea works. Because you are pushing data all the way through, you can dictate what data goes into the open resolver. And then, if you set a very long expiry date inside that thing, you can actually then start using that open resolver as file storage. Which is kind of unholy. Maybe that shouldn't be a thing, but it actually turns out you can write this. And I had a giant list of open resolvers that did correctly hold on to data. So I did. This is roughly the GIF demo of this. So it's running not actually running as a fused file system. Instead, I wrote a HTTP service because it's way easier to write those. So in this case, we have a previous blog post of mine. I'm just uploading it through curl into this service. In the background is Wireshark, so we can see the traffic going across the network. As you see, a bunch of DNS packets are sent out. And in a moment, yeah. So you can see, like, basically, the only thing that happened here was a lot of DNS queries from various weird IP addresses. And then, hopefully, GIFs don't move as fast when you, like, explain them. So yeah, and then we asked for them again. And then not using any other information other than the fact that we have an algorithm to figure out which IP addresses probably had that file. We just go and query those resolvers again, and we have retrieved the file back, or we have retrieved a file back. And then later on we check that the MD hash sums are correct. And yeah, they're the same, which is, yeah. And, you know, some systems have firewalled me out, but that's fine because this program replicated things 3 ways to ensure reliability of your files. Yeah, probably. So yeah, anyway, next hack. Border Gateway Protocol. So Border Gateway Protocol, I'll do a brief explanation because it's not entirely obvious how BGP actually works. People throw around the word BGP a lot without fully, I think, understanding what it does. So, you know, you have a router. It is in the routing wilderness, though, because it is just a router on its own. Except routers' jobs are to, like, you know, shuffle packets along multiple Ethernet lines. And so, you know, we add its friend. The problem is routers need to also know where things are. They need to have a view of the internet. And so in this case, you know, we're just saying that, you know, this router owns the red resource and the other one owns the blue resource. And we're just imagining that a protocol says, you know, hey, can you send me, you know, when you have packets for blue, can you send them to me? And the other one, you know, returns the favor and says, yeah, sure. When you also have packets for red, send them to me. This thing scales out. So in this, you know, in this direction, we have lots of routers all connected to each other in different varying directions. If one says, hey, this letter or this address is mine, it will tell its friends, which should also tell its friends, who also tell their friends. And at the end, you get a route, or at least all the routers in the world should know a path towards the destination. And if they're set up, or if best common practice is followed, you have 2 internet connections. So they have multiple paths to this destination that they can use in case one link goes down or one ISP just can't reach it anymore. Which occasionally happens due to, like, cable failures. This is what, like, if you were to query on a BGP router, like what it looks like. You have a IP address at the top, and a bunch of information. The AS path is what networks you're hopping through to get to that destination. There's also something else here, called a BGP community. What that is basically a 32-bit number that the world of networking engineers split in half because they didn't want to just have a blind 32-bit number. So they said, the first half is the network identifier, and the second half is just arbitrary data. There are no standards. There are a few special reserved bits of arbitrary data that you can pick to do certain actions, but there's only 2 or 3 of them. And the rest is basically just up to you. And so they mean different things on networks. So for the previous example, this means that the first one means that it came from London, you know, it came from the customer. You can learn about various things and you can make decisions on it. So for example, if you have an internet connection in London for this ISP, and you know that this ISP is only really good for, you know, clients inside London, you may only want to use that internet connection for clients that they have in London. Because, you know, let's say if you needed to suddenly make a change for a cable break or something, this could be really useful. So I was thinking arbitrary data, which means you can do data transfer over it very slowly. So I was thinking you could probably play Battleships with this, right? If you had two ISPs playing along. So this format was brought up. You have a counter so that systems always know that they haven't moved backwards or played again. And there's a position community, which, Battleship is a 10 by 10 grid, so you only need 4 bits to represent the entire grid. And then you also have a hit or a miss counter to let the previous side know whether their attack worked. And afterwards, this is what it looks like. So, relatively innocuous numbers. A network engineer would just be like, that's arbitrary data. No one has any decent documentation of what each other's community numbers mean. So this would fly totally under the radar. And so me and a friend played Battleships across the Atlantic. My router was in London and his router was in New York. And it took approximately 10 or 15 seconds to move a route update across the across the Atlantic, because these things are not designed for high performance. I eventually won. Important information. Total abuse. We did some serious sins here. Basically all of the expensive routers in the world knew about this game, and had to process the fact that we were playing this game every 15 seconds. We're ultimately really abusing the routing protocol at this point. We're using the routing protocol to transfer that controls the flow of data to transmit data in the routing protocol, which is a little bit unholy. Can we imagine the abuse emails? 0 star. Level 3 automatically banned me for 20 minutes for updating my routes too much. So that was inconvenient. The game had to be stopped for 20 minutes while we just waited it out.
Did you figure out what the period is that you could play your game without getting banned?
The question was, could we figure out what the period is for without getting banned? I foresaw this was going to happen. And so we made a rule of like a cooldown period of not playing after like 30 seconds after you play a move each. It turned out this wasn't enough. And we had to upgrade it to I think 90 seconds to be sure, once level 3 unbanned us again. However, obviously, even though we got 0 abuse emails, although we did get automatically banned by an entire international ISP, this wasn't like without consequence. I thought it was kind of amusing that, there are a lot of routers in the world and they consume a lot of power, right? So this is a supervisor card. A router would probably have 1.25 of these on average. Some routers have multiple ones for redundancy. Other ones for companies they don't care, or they have multiple units themselves. My guesstimate would say that there's probably 1.25 on average of every router out there. Each of these supervisor cards are basically full-on computers, but with FPGAs in them, and so they consume an extra amount of power under load. So each one consumes about 700 watts just sitting there, which is pretty brutal. And a properly set up router could take up to 30 milliseconds to process a message from BGP in CPU time. So it's just a case of figuring out like the numbers now, right? So the ISP we were playing this through, which was level 3, has about 7,726 downstream networks. Probably have like 1.5 routers on average. Some of them will be really small. Some of them will be really big. We'll have multiple routers inside the network. Ultimately, I'm just trying to figure out on average, like how many routers are we talking about that saw this information? It also doesn't help that level 3 themselves have a giant network. This is just the US alone. Each one of these dots definitely means at least one router, one of these like dual 700 watt beasts. This is what the network looks like in Europe. It's also pretty dense. The same sort of deal looks like the same in Asia, and South America as well. Rough count, they have about 721 internal routers. So you can start doing maths and say, we roughly consumed that amount of kilowatt hours per update we did. You can multiply that by the amount of moves we did and how many routers are involved, and you end up with about 0.04 kilowatt hours, which is a meaningless number because you have nothing to really compare that to. So I give you a hamster. It's about 25 grams of meat, 35 calories, assuming the entire hamster is made of meat, which it is not. So actually, it's probably multiple hamsters, to be honest. But yeah, roughly, we burnt a hamster or two worth of electricity. And that's also assuming that the conversion between hamsters and electricity is 100% perfect, which I don't think we have that technology yet. I think it's time for me to stop. Thank you. Questions? I dare?
Yeah.
Go ahead.
The numbers sometimes about the power estimate that your Battleship game used. Was that just the level 3 routers, or was that all the routers in the world combined?
You mean the wattage on the supervisor card? So pretty much everyone just uses the same equipment.
Okay.
So it'll either just be a Cisco piece of kit or it'll be a Juniper piece of kit. They don't really compete.
The estimate on the next slide applies to all carriers worldwide, not just level 3.
Oh, so the fun quirk about this is that level 3 probably wouldn't have told the other networks about the game, because one of the unwritten rules of these large networks is they don't transmit community strings between each other, which is really annoying, and we discovered while planning for this thing, and it really screwed us over. So we had to move specifically to level 3 because they were one of the only ISPs that didn't do this.
Yeah.
Wait, so if I get it correctly, you in the UK and your friend in New York were connected via the same
Primary provider. Yeah.
Okay.
Or we had an easy path to that primary provider.
Okay, otherwise it wouldn't have transmitted it?
Otherwise, yeah. So had the route not made its way to level 3, I don't think... there may be another ISP, there may be another major international ISP out there that does this trick, but I couldn't find one, and level 3 was the easiest one that we could both get access to. And so we just picked level 3. The other popular ones like Cogent, NTT, GTT, etc., just strip it coming in, because I asked around for some of the old like Bell Labs people on what like the actual world opinion of this is in terms of networks, and the general consensus is networks should not transmit these pieces of information between other networks. They should just be ephemeral pieces of information. That's clearly not the case, because if we look back here, like there's all sorts of stuff going on here. But
maybe someone else is playing a game.
Yeah, most of it is just like side pieces of tagging information from the major ISPs themselves. But yeah. Yo.
How did you tell? How were you informed of your ban?
Everything. So the question was, how was I informed of the ban? Everything just stopped working. So obviously me and my friend weren't just entirely communicating over BGP. We were talking over a text chat. And when I played a move, we would say when we were both playing moves, so that we could time how long it took to get the data across the Atlantic. And we played a move, and it just didn't turn up on the other end. And then we did some further digging into like level 3's internal network, and found that we were banned. Well, I was banned.
How far were you banned? As in, did your complete internet stop working?
No, so level 3 had completely just dropped me from the inbound path. But that's fine, because that just means level 3 will take another route to a major provider. So level 3 customers accessing my network were inconvenienced. And likewise, I was inconvenienced, assuming that the network was only on level 3. Cool. Thank you very much.